All right, in this video, I want to introduce two other rules for differentiation, shortcuts that it turns out that we can use. You may remember that with limits, there were some limit laws. We learned things like a constant multiple rule, that you can pull a constant multiple out of a limit, and a sum and difference rule that says that the limit of a sum is the sum of the limits, and similarly for differences. Those rules for limits essentially sort of carry forward. And derivatives, because they're defined, because the derivative is defined in terms of limits, it sort of inherits those properties, as if you will, from limits. So I'm going to show you how that works out, and I'll show you what the rules look like, and then I will show you how we can put them to use. So first of all, let's look at this constant multiple rule. So in this situation, we're imagining we have some function f of x. Doesn't really matter what it is, just some other function f of x, and we're multiplying it by a constant c. I've put the constant in red here. So this is what it would look like if you set up the limit of the difference quotient for this, the resulting function you get, constant multiple of f of x. Now, that constant multiple, we could factor it out. We could factor it out of this entire thing here. So we could pull out the c here into the front like that, and then have times this fraction f of x plus h minus f of x all over h, like that, with the limit. And then we can use that constant multiple rule for limits that says, hey, if you have a constant multiple of the function, you could make it the constant multiple on the outside of the limit instead. I'll pull it out over here. And then what's left inside here, this is just the derivative of f of x. Like all of this here is just f prime. So in fact, if you have the derivative of c times f of x, this is just c times the derivative of f of x. So just like with limits, you can essentially take a constant multiple and kind of pull it outside of the operator. Limits are an operator, derivatives are an operator. So it works very similarly. Now, what if you have two functions added together? Start with adding, and then we'll also look at what it looks like if it's f of x plus g of x. Using this whole thing as your function, setting up the limit of the difference quotient would look like this. Here's the function applied to x plus h. Here's the function applied to x. We're subtracting. I have parentheses here that are very important. All over h. All right, so the first thing I'll do, I guess, is go ahead and distribute that that subtraction there. So we're going to have, I'm going to go ahead and omit the parentheses on the left side here. And we're going to have minus f of x and minus g of x. Okay. So next, I'm just going to do a little bit of rearranging. Let's take the f parts and put them together, the g parts and put them together. And then I'm going to sort of combine two steps into one just to save time here. You can try it yourself, go a little more slowly if you want to fill in the details. But I'm not only going to rearrange the terms in the numerator, I'm also going to split it into two pieces and divide each piece by h. So what I'm going to have is f of x plus h, there's that part. And then I'll put the minus f of x, and I've got all of that divided by h. And then that plus another fraction where I've got g of x plus h, there's that part, positive, minus this g of x, minus this one, and all of that divided by h. And now we can use the fact that limits distribute, so to speak, distribute over addition. That was the sum rule for limits. So again, so this we're kind of leaning on that, what we already learned, right? You end up getting, let me kind of just do it like this here. I'll say if you split this over the limit, you get that, and split it here and put another limit here. And this is f prime of x, and this is g prime of x. And they're just added together. There's that plus, right? That red plus that I've been keeping track of the whole time. So what we have up here is this just becomes a derivative of f of x plus the derivative of g of x. There we go. So there's some boxes around these two things. These are our rules. There's our constant multiple rule. There's our sum rule. You may be wondering what happens is if this sum is a difference. No problem. It works just as well. If this were a minus, this would also end up being a minus. And you can go through and confirm for yourself that all the signs work out so that ends up being a minus. All right, so these are pretty handy. They give us ways of combining some things together or multiplying them by constants. And in particular, one thing that this allows us to do is to differentiate any function. So let's say you have a polynomial like 4x to the power 3 minus 2/3 x squared minus 10x plus 3.8. I made up a polynomial. Okay, let's have that be our f of x. If we want to find f prime, we want to take the derivative of this entire thing, right? Well, let's do that. Oops. Well, first of all, we can apply the sum and difference rules. We can apply that and split up this differentiation over each term. Ooh, it's getting long. All right. So now I'm doing the derivative of each term individually. Then we can apply the constant multiple rule. I'm going to move over here a little bit. Each of these has a constant multiple. This is a constant multiple. This is a constant multiple. This is a constant multiple. And this is a constant multiple. So I can pull those constant multiples out. 4 times the derivative of x cubed minus 2/3 times the derivative of x squared. And then minus 10 times the derivative of x plus 3.8 times the derivative of, you guessed it, 1. So now, what have I learned? The power rule. So now I've split this up, and each of these things is just the derivative of like some individual power function, right? Each of these. To each of these, I can apply the power rule, right? So what happens? 4 times. Here I apply the power rule and get 3x squared minus 2/3 times. Here I apply the power rule and get 2x to the power 1 minus 10 times. Here I apply the power rule and get, this is x to the power 1, so I get 1 times x to the power 0, which is just 1 itself. This part's just 1. And then here I get 3.8 times, if the reason I say you can use the power rule on this is because 1 is kind of like x to the power 0. So if you apply the power rule, you get 0 times x to the power -1, but it doesn't really matter because you're multiplying by 0. The whole thing is times 0. You may remember in previous video, I explained that the derivative of 1 is 0. If you think of 1 as x to the power 0 and apply the power rule, you'll get the same answer. So in a way, it's kind of like you could have used the power rule on that right from the beginning. But of course, the answer is obvious without the power rule, so we don't really need it. But there we go. There we've split up the derivative, we've pulled the constants out, we've applied the power rule to each part, and now we have an answer. 12x squared minus 4/3 x minus 10 plus 0. And that's the derivative. Now, starting with f, now we have f prime. That's kind of a lot of work, and you do not need to go through all those steps. So I'm showing it to you now so you can see how these rules together with the power rule allow us to differentiate any polynomial function. But now that I've shown that to you, try it yourself, But from this point on, I'm expecting you won't go through all of those steps. Pretty soon, I want you to be at the point where you can just look at this function and say, I know how to do the derivative of that. I'm just going to do the power rule of each term. And you can write down this answer without showing any work at all. You'll be there. You'll be there very soon. You might be there already. So that's my goal for you, is to get you comfortable enough with these basic rules that you can apply them and get derivatives quickly and easily. But we're only a little bit farther down the iceberg. There are some more differentiation rules we have yet to learn. For example, what do you do when you when you need to take the derivative of a product, two functions multiplied together? We haven't even talked about that.